Welcome to the series of e-learning modules on problems with restrictions on capital and problems with restrictions on space. By the end of this session, you will be able to explain the EOQ model with warehouse space constraints, explain the EOQ model with investment constraints. Let us start with an introduction. Effective inventory management allows a distributor to meet or exceed customers' expectations of product availability with the amount of each item that will maximize their company's net profit or minimize its total inventory investment. Effective inventory management is the result of outstanding inventory control and inventory management. Difference between inventory control and management is as follows. Inventory control is managing the inventory that is already in your warehouse, stockroom or store. That is, knowing what products are out there and how much you have to have each item. Knowing exactly where each piece of each product is located in your warehouse. Ensuring that all inventory remains in saleable or usable condition. Storing products to minimize the cost of filling customer orders. On the other hand, inventory management is determining when to order products, how much to order, and the most effective source of supply for each item in each warehouse. That is, ensuring that you have the right quantity of the right item in the right location at the right time. Inventory management includes all of the activities of forecasting and replenishment. The inventory models with one item are considered to be independent of all items being carried in the inventory. Such an arrangement of controlling inventory of each item is only possible if there are no constraints or limitation on the total average inventory. These include the total warehouse space, the total investment in inventories, the total number of orders to be placed per year for all items, number of deliveries which can be accepted, size of delivery that can be handled, etc. Thus, some modification to the optimal order quantity determined has to be made in order to take care of such constraints. The EOQ thus needs to be calculated separately for each item to minimize the total inventory cost under the given constraints of limited warehouse capacity and finance. The following assumptions and notations will be used to develop inventory models under various constraints. The assumptions are: production or supply is instantaneous with no lead time, demand is uniform and deterministic, shortages are allowed. Notations are as follows. N is total number of items being controlled simultaneously. Fi, floor area or storage space required per unit of item I, where I is equal to 1, 2 up to n. W is warehouse space limit to store all items in the inventory. Lambda is non-negative lag range multiplier. D of I is annual demand for ith item. Q of I is order quantity for item I in inventory, where I is equal to 1, 2, 3 up to n. M is the upper limit of average number of units for all items in the stock. C of I is price per unit of item I, where I is equal to 1, 2 up to n. F is investment limit for all items in the inventory in rupees. Now coming to the EOQ model with warehouse space constraint model. The use of inventory control procedures is critical to maintaining accurate, reliable numbers for your operation. Control can be complicated balancing from the time a stock order is placed, received at your warehouse, counted, verified, labeled, put away, picked and shipped out or picked up. Knowing where your product is with accuracy at all times is vital to your success. You can control your stock of products by installing a system of inventory control procedures. Follow your inventory from the first moment the product arrives at your door until it leaves your facility. Assume that if the warehouse space required for per unit of an item I is Fi, then the total floor area required by all the inventory items must be less than or equal to the total floor area of the warehouse. This can be represented by summation of I is equal to 1 to n into Fi into Qi, which is less than or equal to W. This constraint indicates that even if all items reach their maximum inventory level simultaneously, the warehouse space should be sufficient to store the inventory of these multiple items. One of the key assumptions in the warehouse space management is that it is assumed that all these items are received together. Thus, the problem to minimize the total variable inventory cost for each item together under warehouse capacity constraint, the same can be represented by minimum of total variable inventory, that is TVC cost is summation of I equal to 1 to n into di by Qi into COI plus Qi by 2 into CHI, which is subject to the constraints summation of I equal to 1 to n into Fi into Qi less than or equal to W and Qi greater than or equal to 0 for all values of I. Now next, coming to the Kuhn-Tucker necessary and sufficient conditions for optimal value of TVC. In order to determine the order quantities for different items so as to achieve minimum value of TVC, we use lambda as the non-negative lag range multiplier. This non-negative lag Rangian fraction is given by L of Qi lambda equal to TVC plus lambda into summation of I equal to 1 to n into Fi into Qi minus W. Necessary conditions for L to be minimum are delta L by delta Qi is equal to di by Q square into COI plus half into CHI plus lambda into Fi, which is equal to 0, or in other ways to represent Qi star is equal to square root of 2 times di into COI divided by CHI plus 2 into lambda into Fi. Delta L by delta lambda is equal to summation of I equal to 1 to n into Fi into Qi minus W equal to 0. Lambda indicates an additional cost related to the storage area used by each unit of the item. Since Qi star and lambda values are interdependent, a trial and error method is used assuming different values of lambda in order to satisfy constraint equation on the availability of storage space W. The algorithm. Step 1. For lambda equal to 1, compute the EOQ for each item separately by using the formula Qi star equal to square root of 2 times di into COI divided by CHI plus 2 into lambda into Fi, where I is equal to 1, 2, 3 up to n. Step 2. If Qi star, where I equal to 1, 2, 3 up to n, satisfies the condition of total storage space available, then stop. Step 3. Increase the value of lambda if the value of left hand side of space constraint is more than available storage space, otherwise decrease the value of lambda. This means that the only way of finding appropriate solution is to adjust lambda relatively until the space required comes exactly or very close to the available storage space. Let us look at the problem. Example: A shop produces 3 machines parts 1, 2, 3 in lots. The shop has only 650 square feet of storage space. The appropriate data for the 3 items are given in the below table. In the following table, second row indicates the demand rate of 3 machine parts. Third, fourth and fifth row indicates the procurement cost, cost per unit and floor space required for 3 machine parts respectively. The shop uses an inventory carrying charge of 20% of average inventory valuations per year. If no stockouts are allowed, determine the optimal lot size for each item under the given storage constraint. Now coming to the solution. For lambda equal to 1, computing Qi star where I is equal to 1, 2, 3 for each item is as follows. Q1 star equal to square root of 2 into 5000 into 100 divided by 0.2 into 10 plus 2 into 0.7 equal to 542 units. Q2 star is equal to square root of 2 into 2000 into 200 divided by 0.2 into 15 plus 2 into 0.8 equal to 417 units. Q3 star is equal to square root of 2 into 10,000 into 75 divided by 0.2 into 5 plus 2 into 0.4 equal to 913 units. Therefore, the total space requirements would be summation of I equal to 1 to n of Fi into Qi star, which is equal to 0.7 into 542 plus 0.8 into 417 plus 0.4 into 913 equal to 1078 units, which is greater than the 650 square feet available storage space. The requirement is much above the maximum available storage space. Computing the above for lambda equal to 5, we get Q1 star equal to 333 units, Q2 star equal to 270 units and Q3 star equal to 548 units. In this case, the storage space is 668.3 square feet, which is slightly more than the total available space of 650 square feet. If we use the value of lambda equal to 5.4, the total space is 649.6, which is below the total available space. Now coming to the EOQ model with investment constraint. The need to control cost is of major concern to all types of business. One of the primary controllable costs for business, both retail and manufacturing, is associated with inventory investment and management. These costs include both acquisition cost and the related holding period cost. Holding period costs include items such as insurance, storage and taxes. The holding cost can also include the time value of money. Thus, firms that finance inventory purchases may have higher inventory holding cost and therefore gain more by minimizing the holding cost. In a competitive market, cost containment goals can be attained by keeping inventory to a minimum level. In effect, maintaining inventory levels adequately minimizes the total cost. Inventory represents a substantial investment capital for many firms. Thus, the decision maker places a limit on the amount of inventory to be carried. The inventory control policy must then be adjusted to meet this objective if the total investment exceeds the limit. Suppose the inventory is controlled by a reorder level control policy, that is Q systems, under the conditions of demand and lead time certainty. If a monetary limit is placed on all items carried, then we can state that sigma of I equal to 1 to n into Ci into Qi is less than or equal to F. The problem is to minimize the total variable inventory cost under the investment constraint. Min of TVC is equal to sigma of I equal to 1 to n into di by qi into COI plus qi by 2 into CHI, subject to the constraint that summation of I equal to 1 to n into Ci into qi less than or equal to f into qi greater than or equal to 0 for all values of I. Now coming to the Kuhn-Tucker necessary and sufficient conditions for optimal value of TVC. Let lambda be the non-negative Lagrange multiplier, then the Lagrangian function becomes L of qi lambda equal to TVC plus lambda into sigma of I equal to 1 to n into Ci into qi minus f, where lambda greater than or equal to 0. The necessary conditions for L to be minimum are delta L by delta qi is equal to minus di by qi square into COI plus half into CHI plus lambda Ci, which is equal to 0, or in other ways to represent qi star is equal to square root of 2 times di into COI divided by CHI plus 2 into lambda into Ci. Delta L by delta lambda is equal to summation of I equal to 1 to n into Ci into qi minus w equal to 0. Now coming to a problem example. A shop produces 3 machine parts 1, 2, 3 in lots. The demand rate for each item is constant and can be assumed to be deterministic. No back orders are allowed. The pertinent data for the items is given by the following table. In the table, second row indicates the carrying cost of 3 machine parts. Third, fourth and fifth row indicates the setup cost, cost per unit and yearly demand of 3 machine parts respectively. Determine the approximate economic order quantities for 3 items subject to the condition that the total value of average inventory levels of these items does not exceed Rs 1000. Now coming to the solution. For lambda equal to 1, computing qi star, where I is equal to 1, 2, 3 for each item as follows. Q1 star equal to square root of 2 into 10,000 into 50 divided by 20 plus 2 into 6 equal to 177 units. Q2 star equal to square root of 2 into 12,000 into 40 divided by 20 plus 2 into 7 equal to 168 units. Q3 star equal to square root of 2 into 7,500 into 60 divided by 20 plus 2 into 5 equal to 173 units. Based on the above values, the investment over the average inventory at any time is given by summation of I equal to 1 to 3 of Ci into Qi by 2 equal to 6 into 177 by 2 plus 7 into 168 by 2 plus 5 into 173 by 2 equal to Rs 1551.5 greater than Rs 1000, which is the fund available. This requirement is more than the maximum fund available. Therefore, conducting another trial with lambda value equal to 4, we get the corresponding investment on average inventory to be Rs 1112.5, which is also slightly higher than the fund available, which is Rs 1000. If we use the value lambda equal to 4.7, then we get the corresponding investment on average inventory to be Rs 999.50, which is very close to the available fund, which is Rs 1000. Now coming to the EOQ model with average inventory level constraint. Since the average number of units in the inventory of an item I is Qi by 2 and it is required that the average number of units of all items together held in the inventory should not exceed the number m. Therefore, we must have half into sigma of I equal to 1 to n into qi less than or equal to m. The problem of minimizing the total variable inventory cost under the total average inventory constraint can be formulated as min TVC equal to sigma of I equal to 1 to n into di by qi into COI plus qi by 2 into CHI, subject to the constraint half into sigma of I equal to 1 to n into qi less than or equal to m and qi greater than or equal to 0 for all I. Following the same argument as discussed in the earlier model, we can derive the following Lagrangian function as L of qi lambda equal to TVC plus lambda into half into sigma of I equal to 1 to n into qi minus f, where lambda is greater than or equal to 0. The necessary conditions for L to be minimum are delta L by delta qi is equal to minus di by qi square into COI plus half into CHI plus lambda by 2, which is equal to 0, or in other ways to represent qi star is equal to square root of 2 times di into COI divided by CHI plus lambda. Delta L by delta lambda is equal to half into summation of I equal to 1 to n into qi minus m equal to 0. Now coming to the problem example. A shop produces 3 machine parts 1, 2, 3 in lots. The shop has only 560 square feet of storage space. The appropriate data for the 3 items are given in the below table. In the following table, second row indicates the demand rate of 3 machine parts. Third, fourth and fifth row indicates the procurement cost, cost per unit and floor space required for 3 machine parts respectively. Determine the optimal number of units for each item separately so as to satisfy the given constraint. Coming to the solution. Compute the values as done earlier. For lambda equal to 1, computing qi star where I is equal to 1, 2, 3 for each item is as follows. Q1 star equal to square root of 2 into 5000 into 100 divided by 0.2 into 10 plus 2 into 0.7 equal to 542 units. Q2 star is equal to square root of 2 into 2000 into 200 divided by 0.2 into 15 plus 2 into 0.8 equal to 417 units. Q3 star is equal to square root of 2 into 10,000 into 75 divided by 0.2 into 5 plus 2 into 0.4 equal to 913 units. For lambda equal to 5.4, we get Q1 equal to 324 units, Q2 equal to 262 units and Q3 equal to 531 units. The average inventory level then becomes half into whole bracket of 324 plus 262 plus 531, which is equal to 559 units, which is very close to the required average inventory level of 560 units. Thus, Q1, Q2 and Q3 are the optimal quantities of the 3 items respectively. Now next coming to the EOQ model with number of orders constraint. There is a general approach what is not optimal but is considered reasonable. It is used to find EOQ in case of multi-item inventory. Problem with a constraint on the number of orders to be placed per year. This approach can also be used where ordering cost per order and carrying cost per unit per time period are not known. However, it works with the following assumptions. Ordering cost and carrying cost are same for all items. Orders are received in lots. Demand is constant and stockouts are not permitted. Under the above assumptions, the total number of orders per year, that is N equal to D by Q for all items, can be determined as number of orders per year equal to N into square root of DC divided by sigma into square root of DC, where DC is equal to demand in rupees and N, which is equal to specified number of orders. Now coming to the problem example. A company has to purchase 4 items A, B, C and D for the next year. He projected demand and unit price in rupees are as follows. In the following table, first column represents the items A, B, C and D. Second and third column represents demand and unit price of the items respectively. If the company wants to restrict the total number of orders to 40 for all the 4 items, how many orders should be placed for each item? Coming to the solution. The computation of 40 total orders per year to 4 items are calculated as follows. First, let us calculate the square roots of the demand and the consumption for each item. For item A, it will be 60,000 into 3 is equal to 1,80,000, whose square root is equal to 424.26. For item B, we will get 40,000 into 2 is equal to 80,000, whose square is equal to 282.84. For item C, we have 1,200 into 24, which is equal to 28,800, whose square is equal to 169.70. For item D, we get 5,000 into 4 is equal to 20,000, whose square is equal to 141.42. Summation of square root DC is equal to 1018.22. Next, we will calculate root of DC divided by summation square root of DC. So, for item A, we get 0.416. Item B is equal to 0.277. For item C, we get 0.166. And for item D, we get 0.138. Next, we will calculate the number of orders per year, which is equal to N into square root of DC divided by summation of square root DC. So, N here is equal to 40 orders per year, and taking the values in column 5 of the table, we get the values as follows for item A. 16.64, which is approximately 17 units. For item B, we will get a figure of 11.08, approximately 11 units. For item C, it is given as 6.64 approximately, giving around 7 units, and item D is equal to 5.52 approximately, which is around 5 units, and the total of the units will be equal to 40 units. Now finally coming to the summary. Here's a summary of our learning in this session, where we have understood the EOQ model with warehouse space constraints and the EOQ model with